Hey everyone, happy Wednesday. 2 more days to go. Hope you guys are going to be able to make it. So today we want to talk about the math behind the Le Chatelier's principle. So yesterday we talked about how a reaction will shift if we apply a stress to it. And today I just want to talk a little bit about why that is, right? What's happening if we look kind of at the math behind it, okay? And so we're going to look at a couple different scenarios here. And so the first one, we have this lovely equilibrium between iron 2 oxide and carbon monoxide goes to iron plus carbon dioxide. And we see Kc for this particular reaction is 0.263. Okay, and so let's just say that we start with a container, and in that container we put in 10 grams of our FeO, and we put in some CO2, or I'm sorry, some carbon monoxide, and we're going to start with a 0.25 molar concentration. Now, if we do this, right, we know that this reaction is going to develop, right? So we know that these two things are going to react. We know that we're going to produce some in here, some Fe, and we're also going to produce some CO2. And before too long, right, this system will reach an equilibrium. And when we reach an equilibrium, what we see is that the concentration of CO, right, we would expect to go down, and we would expect the concentration of CO2 to go up as we kind of get to that equilibrium. And what we would find is that this would be equal to 0.198 molar, and this is going to be equal to 0.052 molar, again, based on that K value there. If we had more time and we were in the classroom, we would actually do this and try to learn how to calculate what these concentrations would be at equilibrium. But since we don't have time, we'll save that to next year if you guys take AP Chemistry. So now what we know is that when we hit equilibrium, we're going to have that, right? And if we kind of look at that, we know that if we take that concentration of our CO2, which is 0.052, and divide that by the concentration 0.198, we're going to get that 0.263 because, again, right, that K is just a ratio of those concentrations. Easy enough, all right? Now, what we know, like, is this. So let's say that we're at our equilibrium. So let's not worry about these right here anymore. Right now we're going to focus on these values at equilibrium. And let's just say that in this particular system, right, we were able to add more CO. So we increased the concentration of CO. Let's say we doubled it. So that would be 0.396 molar, right? Now, Le Chatelier's principle tells us what? Well, we just increased the concentration of a reactant, and so Le Chatelier's principle tells me that I should see a shift forward, right? And that's what it tells us. Now, the question is, well, why is that? Well, the simple answer is, well, there's going to be more collisions. We can have that, right? But now, mathematically, if we kind of look at that, what we can see is that, well, if we kind of look at that ratio is no longer there. And so mathematically, what we're able to do is we're able to figure out and find something known as the reaction quotient, as you can see here at the bottom of the page. Now, the reaction quotient is something that we can find. It has a Q, right? And what we can do is we find the reaction quotient in the exact same manner as we would the equilibrium constant. So we would have the same exact formula. But this thing we do here is now we could plug in the numbers that we see. So we increase the concentration there to 0.396 molar, right? That's going to be divided by 0.052 molar. And when we do that, we see that number will be 7. Oh, I did that wrong, didn't I? Oop, strike that. Sorry. My bad. let's put those numbers in correctly. So that's still going to be, so CO2 is 0.052 divided by 0.396. Sorry, plugged in the wrong numbers wrong. So let's do this. 0. Divided by my 0.396, and that's going to be 0.131. So now what we can see here is this, that if we look at the equilibrium quotient, if Q happened to equal K, right, then those two numbers are the same, then we know that that reaction under the concentrations that they have inside the container are going to be at equilibrium. But that's not the case, right? In this particular case, we see Q is actually less than K, right? And so if Q is less than K, what that tells us is that the reaction has to shift forward to reach equilibrium. And why does it have to shift forward? Is because, well, it has to shift forward because this ratio has to get bigger, because this reaction doesn't hit equilibrium until the ratio gets bigger. And the only way that we can get the ratio bigger is increase the number in the numerator and decrease the denominator, right? And so that would be that forward shift that little Le Chatelier's principle tells us, right? So that would be this example. But if I kind of look and say, oh, well, what would happen if I should happen to increase the concentration of CO2? Well, if I increase the concentration of CO2, Le Chatelier's principle tells me that I have to shift reverse, right? And in that situation, if I were to increase the concentration of CO2, we would be in this situation here where our Q would be greater than K. And because we would see that the numerator would get bigger, and so that would have us shifting reverse. Okay, so we can compare and we can find out what Q would be compared to K, and that would tell us which way it shifts mathematically. And so that's with concentration, right? We know another stress that we can apply is with volume. So let's say that we had this volume here, right? And let's say that this system is at equilibrium. To make life easy for me, I made up these numbers. So we say for this system that Kp is 4, and now we see that we have an equilibrium mixture where we're looking at the partial pressures. And so now the partial pressures are here for these two things. And if we look again, right, it's going to be, right, products over reactants. So we would get 2 squared divided by 1, and that's going to be 4.0. Right, and so in that particular case, we would see, hey, we're at equilibrium. Now, let's say that we were in a situation where we were able to cut this volume in half, right? And so we kind of cut the volume in half, and so we kind of squished this thing down, right? So when we cut the volume in half, right, we should hopefully make sense that my pressures are going to increase. And so in this case here, this goes up to 2.0 and this goes up to 4.0. Now, Le Chatelier's principle says, hey, if we decrease the volume, thereby increasing the pressure, we should see that it's going to shift to the fewest moles of gas. So in this case, we should see a shift reverse. Well, now if we do this, and again, we can say, okay, well, is this system at equilibrium? So if we take our QP, which is again going to be P of the NO2 squared times P of the N2O4, right? In this case, that would be 4 squared over 2, right, which is 16 over 2, and that's going to be equal to 8. So in this case here, we see now Q is greater than K. And again, when we look back here, anytime that we see Q is greater than K, So we see Q is greater than K, we should get a shift reverse. And so in this case here, Q is greater than K, we should see a shift reverse. So mathematically, we are backing up what we see with Le Chatelier's principle. Okay, so knowing how a reaction is going to shift, right, based on the reaction quotient or based on Le Chatelier's principle can be useful to help make sure that these things are going to maintain. Now, where is this really useful for us? Like, you're like, yeah, so what? Where is it really happening? Is, well, let's say that we do a double replacement reaction or something, and we want to know if a precipitate would happen. And let's say that we are trying to do something like PbI2. And let's say PbI2 has a KSP that equals to, and again, I don't know this, I should have wrote this down, but I didn't. So let's just say it is 2.8 times 10 to the negative 15th. Again, right, if we're talking about KSP, and I say, okay, well, I have PbI2, I know because that's going to be my solid, it's going to go into Bb2 plus 2I minus. And so now I know that my KSP is going to be equal to Pb2 plus, oops, sorry, I lied, no plus in. It's going to be equal to Pb2 plus times I minus squared, right? And let's say, okay, well, I have these two solutions, and I mix these two ions together. And my two ions I mix together where the concentration of Pb2 plus in my solution is 1 times 10 to the negative 5th, and the concentration of I minus in my solution is going to be like 2 times 10 to the negative 3rd. And the question is, hey, if I have these particular ions and I'm mixing them together like this, will I see a precipitate? Will these two ions precipitate out? Well, what I can do again is find Q. Q would equal, again, that 1 times 10 to the negative 5th times 2.0 times 10 to the negative 3rd, and again squared. So that Q is going to be equal to 4 times 10 to the negative 11th, right? And so in this case here, we're talking about this reaction. We see Q is greater than K. When Q is greater than K, we just learned that it's going to shift reverse. And so in this case here, because Q is greater than K, we would expect to shift reverse. And when we shift reversed, we see that that solid should form. So if we had those two ions in those relatively low concentrations, right, we are expecting, according to this method, that we would see a precipitate being formed. Okay, that's how we can use it. There is something that we can do for temperature. It's a little bit more complex, and so we're going to bypass that right now. We will get into it next year in AP Chemistry if you choose to take AP Chemistry. And yeah, so that's how we can use the reaction quotient to kind of back up what we see with Le Chatelier's principle. All right, guys, make sure you're working on the problems. Reach out if you have any questions, and we'll talk to you on Thursday. All right, peace, love, happiness. Thanks for playing.